You may have loved the algebraic derivation of the Lorentz transformations. You may not have enjoyed the algebra. Either way, let's remember the logic. What we did is we assumed 4 facts. One, that if a blue observer is moving with speed v relative to a black observer, then the black observer is observed by the blue one to be moving with velocity minus v. And so relativity works in that way. That was assumption number 1. Assumption number 2 was that motion that is observed by the black observer to be inertial, in other words, to have a straight world line, is observed by the blue observer to have a straight world line, in other words, to be inertial. Newton's laws hold in both frames in the sense that if an object is observed to be experiencing no force in one frame, it's observed in the other frame to also be experiencing no force. That was assumption number 2. Assumption number 3 was the statement that the velocity of light is the same in all frames, and putting all those assumptions together, we were ineluctably led to these Lorentz transformations, which, remember, relate the position and time of any event, something happening, a birthday party starting, as measured by one observer, to the position and time of the same event as measured by another observer. 2 observations about this before we go on to derive the consequences of this, which are the meat of special relativity. 2 things to note right off the bat. Observation number 1 is if you look at this denominator, you notice that if v squared over c squared is bigger or equal to 1, then this denominator is either 0, where you get an infinity, or it's negative and the radical is imaginary. What we conclude is that if you put together our modest assumptions, which we're going to assume as part of physics, along with the idea of 2 observers moving relative to each other with a speed larger than the speed of light, you get nonsense. Conclusion, since we're not going to abandon relativity, 2 observers cannot move relative to each other with speeds larger than the speed of light. The speed v in all of our Lorentz transformations will forever be less than the speed of light. Therefore, when we talk about superluminal motion, you cannot accelerate yourself in any way, and we will see how physics stops you from accelerating yourself to speeds faster than light. So, comment 1. V squared is always less than c squared. Comment number 2 is I worked in a one-dimensional universe. We don't really live in a one-dimensional universe. We live in a 3-dimensional universe, so you can ask what happens to the y and z directions. If the motion is, I can always pick my x direction to point along the direction of motion. What happens in the other directions? Well, in the other directions, life is much simpler. Y prime and z prime are simply given by y and z. Nothing happens. That takes not too much calculation. So all of the action is indeed in one dimension, along the direction of motion. Let's see what happens. Let's follow through. What are the consequences of adopting these Lorentz transformations? By far the most confusing one is this idea of simultaneity. Notice, we are not shocked that when we draw the now and the here of the black observer, and then we draw the here of the blue observer, this describes a tilted world line. Well, good. That's not shocking. We expect, this describes the fact that the blue observer is moving. What is shocking and very confusing is that if you look at the Lorentz transformations, and we look for the collection of all events such that they are characterized by t prime equal to 0, you find that that is not equivalent to t equal to 0, but rather to t equals vx over c squared, so that the blue observer's now differs from the black observers now. They agree, and when I say now, these are all of the events in the history of the universe that each observer imagines to have occurred simultaneously with, in this case, their meeting, because that's how we set t as t prime is 0, is they both started their watches at the moment when they met. And so this violation of simultaneity is the cause of much, much, much confusion and many paradoxes. And to get a sense of it, for first, how much should we worry, let's measure the magnitude of this effect. So, for example, when I am driving in my car, things that I consider simultaneously are not the same as things that a bystander on the sidewalk considers simultaneous if you move far enough out in the direction of my motion. It's a happy coincidence that if I'm moving, say, at 10 meters per second, a reasonably fast clip, then I can estimate that our time, our space axes, or our definitions of simultaneity will differ by about a second for objects that are a light year away. So if something is happening a light year away, and I measure when I think it happened, and I'm driving in my car towards it, and someone standing on the sidewalk measures that time, we will disagree by a second over the distance of a light year, but how are you going to know what's going on right now at a distance of a light year? That's the subject of our next question, so we'll address that in a second. Nonetheless, when you are moving not at 10 meters per second, but at relativistic velocities, this idea of simultaneity meaning something different is significant, and understanding it correctly, or learning to wrap your mind around the weirdness that it is the main obstacle to feeling comfortable with relativity, and that comes from working problems. We'll probably have an optional clip where I will work paradoxes in relativity to give you a sense for how that works. You'll note that when I've drawn these diagrams, I am often drawing the red lines, which are the world lines, remember, of the two light beams, at 45-degree angles. Now, the tilt of the world line from the vertical should correspond to the velocity or the speed with which something is moving. So essentially I'm saying that light moves with speed 1. The way that's typically implemented is that you plot not t, but ct on your diagram. So you're effectively working in units such that the speed of light is 1. In my field, we do that all the time anyway, and so I have to remind myself to put the c's in. The c's will be in all my equations. I do not promise to always remember to plot ct on this plot, but I am indeed plotting ct. And if you remember that what you're plotting is ct, then you can see that the geometry of the situation is as depicted here. The 45-degree world line of a light beam bisects the angle between the time and space axis for any observer. So if you have a green observer who is moving faster than the blue observer, that means their t double prime axis will be tilted farther away from the vertical, then so will their x double prime axis be tilted farther from the horizontal. This is the geometry of the Lorentz transformations that we wrote. So how do we know what's going on a light year away right now? What do we actually mean by right now? Well, now that we understand that the speed of light is a constant, we can give a technical, measurable, operative meaning to what's going on right now. If, for example, 6,000 light years away on the Crab Nebula, something is happening now, well, I don't know it yet, but in exactly 6,000 years, the light from there will reach Earth. So I define what's going on now at the Crab Nebula to be what we will see on Earth in 6,000 years. If I make that definition, that now I have an operational meaning of what the present is, at any distance, things happening now are the things from which we will hear at a time related to its distance from us by this expression. And so if you use that operational definition of what you mean by the present, then following through the behavior of light beams, drawing them onto that diagram that I drew before, you find that this relativity of simultaneity is obviously a fact. It's a property of the fact that light moves at the same speed in all frames. Okay, we'll swallow simultaneity, we'll work through it. It only matters at large distances or high speeds, so the fact that it conflicts with our everyday experience, well, we don't have everyday experience of moving at the speed of light. What other weird things do the Lorentz transformations teach us? Well, for starters, they teach us about something called length contraction, which is a very puzzling property, and we need to understand it, so let's see what it does. How do you measure the length of something? Well, here's the idea. Suppose that the moving blue observer is holding a ruler. This ruler has nominal length L prime. He bought it at a store. It's a 1 meter ruler, so L prime may be 1 meter. He's holding it, and so its left end is in his hand at x prime equals 0. Its left end is a distance 1 meter, L prime, to the right of that. And of course, it's moving with him, and he measures its distance, and he says the distance is L prime. Very good. We want to know what happens if the black observer measures the length of the same ruler. So how do we do that? We turn to our friends, the Lorentz transformations, which contain all of the information. And we use these transformations to understand where the black observer sees the ends of the ruler. So, not too difficult. Let's see what we get. the left end of the ruler is at all time at x prime equal to 0, it's clear from setting this that x prime equals 0 corresponds to x equals vt. So, good. The left end of the ruler is in the hands of the blue observer, and as seen by the black observer, it's moving to the left, to the right with speed v. Good. What about the right end of the ruler? I set x prime equal to L prime, and I get an equation that says L prime is x2 minus vt divided at any time by the square root of 1 minus v squared over c squared. So I can solve this. I multiply through by the square root, erase it here, put it here, and I then move the vt over to the other side, and I find that x2 is vt plus L prime root 1 minus v squared over c squared. Okay, let's write that out cleanly. x1 is this, x2 is this. Well, good. Both ends of the ruler are moving to the right at speed v, because it's at rest in the moving frame. And the distance between them is constant. Good, the ruler is not wiggling. What is the distance between the two ends at any given time? At any given time, this is the distance between the two ends of the ruler. So this is what you'd call the length of the ruler. And so I conclude that the length of the ruler is this number. And since this multiplier here, the square root, is smaller than 1, the ruler's shrunk. I see a shorter ruler than the person moving with the ruler sees. In other words, when you move something fast, its length shrinks along the direction of motion. This is a real effect. Now, of course, relativity says that if the black observer is holding a ruler of length L, and you ask, what length does the blue observer measure for that same ruler? Well, same expression, flip the sign of V makes no difference. The blue observer thinks the black observer's ruler is shrinking. And, of course, these equations are inconsistent. And so what you have to keep in mind is that they mean two very different things. This is the length, as measured by the black observer, of a ruler of length L prime at rest in the blue frame, so moving with the blue observer. This is the length, as measured by the blue observer, of a ruler of length L that is moving with the black observer. Anything, when it moves relative to us, and I don't need an observer for it, the ruler is an observer all by itself, when a ruler moves along its length, it appears shorter. Again, unless the speeds are relativistic, this is not important. When the speeds are relativistic, this is important, and it does happen. So, moving fast messes with your idea of length. It also messes with your idea of time. We know about rulers. Let's think about clocks. So imagine that the moving observer is holding a clock in their hand, and that clock ticks. And we'll select two specific ticks, one at the time of the historic meeting between the two observers at x prime equals t prime equals 0 equals x equals t equals 0, and another one sometime later, say a second. So the moving observer measures the tick of the clock at t equals 0, t prime equals 0, and then at t prime equals 1, or capital T prime. I want to know, what does the black observer think about this moving clock? In this case, it's easier to use the inverse Lorentz transformations, the ones that give me x and t as functions of x prime, t prime. Remember, they're no harder to write down than the other ones. You just flip the sign of v. And so, we're working at x prime equal to 0 in this case, so that's easy. Both terms with x prime are irrelevant for all of this process, because the clock is always at x prime equal to 0. And so I set t prime equal to 0, and I find directly that t1 is 0. Okay, that's good. We agree that the clock was ticking at the same event, which was the meeting of the observers. Excellent, we agree about that. Events are unambiguous things. But then what about t2? Well, t2 is equal, t prime is now blue t prime, pardon me for not respecting the color scheme, but so it goes, divided by 1 minus v squared over c squared. And indeed, if you ask the black observer, when did the clock tick? This is the time when it ticked for the second time, this when it ticked for the first time. Write those down. It is clear that the time interval between those two is a lot longer than t prime. It's t prime divided by this quantity less than 1. The black observer observes the blue clock to be running slow. Of course, by the same relativistic argument we're used to by now, if the blue observer looks at a clock that is stationary in the black frame, he will observe that the black clocks are moving slow. And again, the fact that these two are consistent, just like the fact that the other two length contraction expressions are consistent, is associated with being confused about simultaneity. What you mean by simultaneity in the two frames is different, and that makes it possible for each observer to observe the other's clocks moving slow. We'll deal with that in the paradoxes section, and we'll soon discuss something about why we know this is true. First, let's follow one important astronomical consequence of this. You have Doppler shifts. We describe Doppler shifts, in the traditional sense, as having to do with radial motion. If an object is moving away from me, then each subsequent wavefront that it emits has a longer distance to go, so I get a red shift. If it's moving at me, I get a blue shift. If it's moving transversely, there is no Doppler shift. But now there is. See, the reason for there's a Doppler shift is, imagine that an object that is moving has some atom in it that is vibrating. The period with which that atom vibrates is determined by the physics of the atom, and that physics is invariant because of relativity, and so that atom, at rest in its own frame, is vibrating at exactly the same frequency that the same atom would vibrate when I held it in my hand here at rest in my frame. But when moving, it vibrates with the same rate relative to the clock that I observe to run slow. Thusly, the vibrations of the atom are slowed down by any motion, so there's a redshift. There's always a redshift. The frequency is decreased. The speed of light is constant. The frequency times the speed of light is always, the frequency times the wavelength is always the speed of light. So there is a relativistic redshift that occurs even if, in the case when there is transverse motion. There is no radial motion whatsoever. And this has to do with time dilation. So there's always a redshift. What happens if the object happens to actually be moving radially? Well, then you have this time dilation effect. But that happens independent of the direction. But in addition to this, you have the geometric fact of how far each light front has to go. So you basically multiply the two effects, and you find the relativistic formula for the Doppler shift. Notice that I'm using the astronomical convention here, where the positive sign of V means the object is receding from us. So we've now converted completely to the astronomical radial velocity component. So this is for a radial or longitudinal. I perhaps should have called it radial, because that's what we have called it. And transverse is tangential when looking at a star. So all observations are have a Doppler shift. When an object is moving at us sufficiently rapidly, the blue shift from negative V here can overcome the red shift from this. But this is the relativistic expression for a Doppler shift. Okay, that's a lot to swallow, Ronan. Is this for real? What's going on? The answer is yes. We have a ton of experimental evidence for each and every one of these phenomena. We observe, for example, length contraction when we collide large ions in accelerator experiments. We accelerate, say, gold nuclei to high energies, to velocities close to the speed of light. And these are large objects. Remember, they're hundreds of Fermi across. And when they collide, the collision happens much too fast for relative to the size of these nuclei. And the reason is that as they observe each other, because of their large relative velocity, these things are colliding as essentially pancakes. And therefore, they pass through each other in a much faster time than would the nuclei given their size and the speeds that we know because we know how fast we've accelerated them. Time dilation is something that's measured all the time. If you want to give, we take unstable particles. Unstable particles decay within some time. We put them in an accelerator, speed them up to a large fraction, a substantial fraction of the speed of light, and they last forever. Why? Because their clocks are retarded. Their time is dilated relative to ours, and we can keep muons stable for hours by moving them fast enough. There are more low-speed measurements of this. In fact, the lowest speed, I think, at which this has been successfully measured has been obtained by taking really high-precision atomic clocks, putting one of them on the runway, putting another one on a jet that circumnavigated the globe a couple of times, and then noticing when they landed that the one that was moving fast was, in fact, behind the atomic clock that had been left on the ground. The effects at jet speeds are tiny, so you need very high-precision atomic clocks. There is no doubt that these are all facts. They're counterintuitive. Too bad. We have to change our intuition. Now, how does it happen? Well, the other question is, so you take this ruler. What happened to the rest of the ruler? You had a 1 meter ruler. You're now moving at some large fraction of the speed of... You move it at some large fraction of the speed of light. The ruler is 90 centimeters in length. What happened to the other 10 centimeters? Well, the answer is, what determined the length of the ruler in the first place? Well, the ruler is held together by electromagnetic forces. Electromagnetic interactions, remember these are Maxwell equations, are invariant under Lorentz transformations, which means that they give the same physics if you do Lorentz transformations. Electromagnetic interactions, if you were able to make the detailed calculation of what determines the size of this ruler, would actually predict that it shortens when you move it fast. In fact, Lorentz, when he first derived the Lorentz contraction, the length contraction expression, was not trying to do relativistic physics. He had not adopted Einstein's principle of relativity. He was doing calculations with electromagnetic fields, and he saw that the electromagnetic field of a moving charge appears compressed along the direction of its motion. He was observing that Maxwell's equations know about Lorentz contraction, which is not surprising, since Lorentz contraction follows from the invariance of the speed of light, which is a property of Maxwell's equations. Woohoo! Similarly, build a clock of any kind, and it will run slow when you move it at high speed. In fact, we just did that calculation. For one clock construction, the light clock moving transversely, where we assumed that the speed of light was a constant, we found slowed down by 1 over the square root of 1 minus v squared over c squared. What about the longitudinal time clock? You'll do that in homework. One last thing before we let go of these weird and bizarre consequences of Lorentz transformations. We talked about velocity addition. What happens when you add two velocities? So back to our old picture. We have the blue observer, we have the black observer. The blue observer sees an object, and the object is moving at a velocity which I should properly call u prime. And I ask, at what... but I will call it u, I guess. And I ask, at what velocity will the black observer observe this object to be moving? So again, I draw the world line of the moving object as x prime equals blue u times t prime. I use my Lorentz transformations, plug in this information, and solve for x. So for example, I can do the calculation. X is equal to ut prime plus vt prime over the square root of 1 minus v squared over c squared. On the other hand, t is equal to t prime plus vx prime. X prime is u t prime over c squared divided by the square root of 1 minus v squared over c squared. And what does that tell me? Well, this is equal to u plus v, just as it was in the Galilean case, except with this funny square root there. This is equal to t prime times 1 plus uv over c squared, divided by the same square root. So indeed, x is some number times t. Inertial motion translates to inertial motion. And the number is obtained by dividing this by that. The reason I didn't write out the square roots is because they happily cancel. I see that x is in fact not u plus v times t as it was before, but u plus v over 1 plus uv over c squared. This is the new velocity addition formula. Let me write it cleanly. Here's the new velocity addition formula. And here I've remembered to put u prime. And what is the great property of this? Well, if u and v are both small compared to the speed of light, if you're dealing with slow-moving objects, then you can erase this u over c times v over c, and you're back to Galileo. Logic makes sense at the small velocities at which we're used to applying it. The other nice property of this is that if you plug in v equal to c, if you ask, if I add some speed, if I observe something moving at a speed c, what will you observe? Well, if v is equal to c, then it's an easy experiment to show that if, v isn't always less than c. If u prime is equal to c, then u is equal to c. So this has the property that on the one hand, at low velocities, it's Galileo. On the other hand, light travels at the speed of light, no matter who's measuring it. These are the consequences of Lorentz. We can play with, if you'd like, you can go on from here to play with some simultaneity puzzles. And if not, we'll move on to constructing relativistic physics.